All right, I think that is everyone for now. So again, thanks everyone to this installment of Paleo Perks, this time on a Wednesday, at least Wednesday for me. And today we have a talk by Juliet Sefton from the University of Melbourne in Australia, who is going to talk about late Holocene sea level change recorded by mangrove sediments in Oceania. So the format of today's seminar, especially if you're new here, we have the welcome and announcements. That's what I'm doing right now. Then we'll have Juliet's talk for around 30 minutes, followed by a moderated Q&A. Don't forget your questions. It says to the questions at PaleoPerks host, but we don't have a questions host today, unfortunately, so you can send them to me or put them directly in the chat. And after that, Juliet has agreed to stay for tea time. So if you just want to have a little informal chat that's not recorded or anything, you can turn your camera on. Then we can also do that and stay after the talk. So then before we get started, a bit of housekeeping. So PaleoPerks values the participation of all folks interested in the paleosciences. So please remember to abide by a code of conduct during today's seminar. Also, please keep yourself muted during the talk out of respect to the speaker. You should not be able to unmute yourself, but if you do find yourself unmuted, please mute yourself again. And as I mentioned, you can ask questions by sending the question privately to me or send them directly in the chat. Or if you want to ask the question yourself, then you can also use the raise hand function and then I will unmute you. If you have any technical issues, you can also send them to me. We have closed captions built into the Zoom. So at the bottom of the screen, there's a CC button, and you can use this to either hide or show the captions. And then finally, we're always looking for more speakers. So if you know an outstanding early career researcher, that can also be yourself. Feel free to nominate someone here. I will drop the link later in the chat. And then finally, we're also always looking for weekly feedback for demographic info, anonymous, optional. And it's very encouraged so we know what kind of people are joining and what we can improve. So now about the speaker, Juliet. Juliet Sefton did her bachelor's and master's in geology at the Victoria University of Wellington in New Zealand. She went on to do a PhD at Durham University in the UK, followed by a postdoc at Tufts University in the US. She then was a lecturer for a bit at Monash University back in Australia. No, not back in Australia. And now she is also in Australia, but as a research fellow and lecturer in the School of Geography, Earth and Atmospheric Science at the University of Melbourne in Australia. So with that, Juliet, I invite you to share your screen and start your talk. Look forward to it.
Okay, I will try and do that shebang again. Let's do it. Okay, yeah. Share the screen. Share. Okay, can you see that okay?
Yeah, looks perfect.
And this is good. Okay. All right. Well, thank you for the introduction. Yeah, it's great to be able to share kind of a bit of what I do, maybe a little bit of my journey and the research that I've just recently kind of finished up and some things that I think about all the time. I'm a paleo sea level scientist, and I'm interested in why and how sea levels changed over hundreds of years and thousands of years. So I typically operate in the Holocene. And I use sediments from all sorts of coastal environments to reconstruct where sea level used to be in the past, using what I like to call geological tide gauges, which I'll talk to you a little bit more about shortly. But I'm going to present to you some work that I've been doing in Oceania, specifically a couple of islands in Micronesia, which is kind of a little place just north of Papua New Guinea. And I'll walk you through kind of how I use paleo techniques to understand these past sea level changes, and then also what past sea level changes can tell us about. And we'll go through things like all sorts of geophysical processes, some past human societies, and maybe some climate sort of sea level stuff over sort of Holocene timescales as well. I I won't dwell on this too much because this is kind of, preaching to the choir here. And this is often how a lot of us paleoscientists try to justify the work that we do. We do really cool work regardless of whether it's about future climate. I think the past is cool regardless. But importantly, sea level is rising, and sea level is going to continue to rise for many, many centuries. And this is the plot from the IPCC report in 2021 with time on the x-axis and meters of sea level rise on the y-axis. And importantly, we can see that towards the end of the century, we have an increase in the uncertainty in what sea level potentially could be, what our type of models can predict sea level potentially could be. So that uncertainty essentially is because we don't actually know how sea level behaves on long-term timescales particularly well. And if we push this out to, say, 2300, which the IPCC does incredibly conservatively in their AR6 report, it could be anywhere from 2 to 7 meters sea level rise under really unlikely but pretty, still feasible scenarios. 15 meters can't be ruled out. So we need to better understand how sea level behaves on long-term timescales. This is particularly related to how ice sheets melt, but this is kind of the justification for paleo research, essentially. So in terms of sea level, then, how we think about this, the instrumental record, we know a lot. We know a lot of these processes. That has been measured by tide gauges and satellites, particularly over the last few decades, but at most 100 to 200 years. And we need to look into the paleo record to kind of target some of these longer term timescales, as you are all very familiar with. So the sea level archive, the proxy that I typically use is coastal sediment, and in particular mangrove sediment. So mangroves are intertidal ecosystems. They're trees that actually have evolved to live in very salty water and that are flooded by the tides twice a day or, relatively regularly. So that means they live in a very narrowly defined environmental niche, typically the intertidal zone, but often even smaller than that, right? And over time, sediment accumulates underneath these forests, and it's that sort of sediment record that's accumulating over time that I'm interested in as a paleo sea level scientist. So I'm going to present to you some of the work that I've been doing in Oceania, specifically the Western Pacific, using such mangrove sediment archives. So we selected 2 sites in the Federated States of Micronesia, which you can see there, Pohnpei and Kosrae. And we selected these sites for a number of reasons, not just because, there's some nice tropical islands we can go and visit, which, people do ask that a lot, but there are some good reasons. So the first one being that Oceania is, at the forefront of climate change discourse, right? And understanding the processes of sea level change in these places is really critical. And the second reason is that, so given that, we're pretty data poor in this area as well. We have a sparse number of tide gauges, so we don't, and also not a lot of geological records of what sea level's done over this time. So this is a good, geographical gap to target. And the other really neat thing about this place as well is being somebody who is interested in mangroves, there are a lot of mangroves in Micronesia. And these 2 islands here, so this is Pohnpei and Kosrae, the mangrove area is what I've shown in the green around these islands here. And previous work by a lot of groups over the last few decades have reported, and particularly for blue carbon and understanding sort of mangrove ecosystem change over time, they've reported up to 4 meters of mangrove peat of Holocene age on these islands. So these are a really good target for paleo reconstructions. And these are 2 islands that, essentially just completely fringed by mangroves. So there's not even any nice beaches we can wash off in. So the argument that we're just going for these cute little fun Pacific holidays, it's just not warranted yet. So I'll take you through then how we actually reconstruct a sea level from mangrove sediments. So a sea level proxy is a biological, a chemical, or a physical feature with a strong relationship to elevation relative to specific tide levels, for example, mean sea level. And we use this relationship to reconstruct sea level from particular features, for example, a mangrove sediment. So in the case of mangroves, we want to know the relationship between where mangrove sediments are deposited and a tidal datum. And we want to know that relationship kind of in the vertical, what the elevation of that is and the elevation distribution of that. Have I got those? Yeah, the elevation distribution of that. So if we find, say, a fossil mangrove sediment, like we do, say, in a sediment core, then we know that at that particular depth in the sediment core where we find the mangrove sediment, this is where sea level must have been in the past, essentially. So what we're interested in doing is quantifying the elevation range that mangroves live in today as distribution, for instance. So trying to find the lower and the upper of that. And that's essentially our uncertainty in our proxy reconstruction. And the other great thing about, oh no, I've got the next slide for that, sorry. So essentially in my line of work, then we do a lot of field work and we survey, by hand often and with like a dumpy level theodolite type methods where mangroves live today and use that modern distribution to reconstruct the past, essentially. This is a picture of my colleague Simon Engelhardt and some mangroves in Samoa. And he's looking pretty happy after actually a very challenging day walking through that mud all day. But it looks nice. All right, so the second step to reconstructing a mangrove sea level curve is collecting the fossil sediment as well. So we collect them as a sediment core, for instance, like you can see on the left-hand side there, and then we take them back to the lab for the analyses. So we want to examine, so we look at it, obviously, and we do a sedimentological analysis on this and say, use our sedimentology knowledge to say, was it deposited in a mangrove environment or not? But we can also use other types of proxies or other pieces of geological evidence to support this. So we can use mangrove pollen, we can use forams, we can use diatoms. So people have tried to use like test-date amoeba and stuff, ostracods, all sorts of little critters that are preserved in these muds. And we can also use geochemistry. We can use things like stable carbon isotopes, biomarkers, and other sort of more elemental analyses as well. And then once we've established that our fossil record is mangrove, then we use a pretty straightforward equation to reconstruct relative sea level from this particular sediment core, which is the altitude or the elevation minus the reference water level being something like mean sea level or high tide or something like that. Relative to where the mangroves are distributed today. And then we represent that as usually as a midpoint and a plus or minus a 95% sort of confidence interval of where those mangroves live today. And that's everything that I was just saying in pictorial form. I forgot that those were there. Anyway, you can enjoy those for a brief moment before I move on. Okay, so step 3. So now we know that where sea level used to be, we know we've got a mangrove sediment, we know what elevation it is now and what elevation range mangrove sediment can potentially form at. We need to know when that was, essentially. And this is just an example of the types of techniques that paleo sea level scientists use, particularly in coastal sediments, to understand when these particular things are. And mostly what I've been using, particularly for this study and what I have done a lot previously, is using radiocarbon to construct our chronologies. So the nice thing about mangrove sediment is it's formed by decomposing mangrove organic matter. So there's a lot of material for us to radiocarbon date, essentially. And then the next step, therefore, okay, we've got when and where sea level used to be, and now we do our proxy reconstruction. And this is essentially the results from this paper I have in review at the moment, and that you've probably seen if you've seen me at another conference over the last couple of years or so. But these are the results from Pohnpei and Kosrae Islands. We have two sites that we did some reconstructions on from Pohnpei and Kosrae, which are the different colors here. But I'll take you through kind of what this plot represents a little bit. So on the interestingly, we don't actually have time. The x-axis labels have disappeared. Sorry about that. On the x-axis, we have time in common era. So the point furthest to your right, it'll be your right, is 0. Well, no, the year 2000, sorry. And kind of the middle of the plot is like 0 common era, so about 2000 years ago. So we have data essentially over the last 3000 years here. And each of these boxes here represents a radiocarbon dated mangrove sediment. And it's a box because on the x-axis, we have our uncertainty from our radiocarbon measurement. And then on the y-axis, we have our uncertainty in the elevation range that mangroves live. So the y-axis representing relative sea level RSL in meters, with 0 being present day. So each of these little boxes represents where sea level was in space and time. And then we can use some statistical methods that incorporate that error in the x and the y to reconstruct essentially a time series of where sea level used to be. And that's what those bold lines are, and those ribbons are around some of that data as well. So the main takeaway from this plot, therefore, so time, and reminding you that time's also going left to right, the correct way, in my opinion. The main takeaway is that sea level was lower 3,000 years ago, and it has consistently risen to present day at all 3 sites that we've reconstructed sea level at in Micronesia. And on Pohnpei, this amounts to about 3.5 meters over the last 3,000 years. And on Kosrae, that's about 2.5 meters over the past 2,000 years. I've also hang on, have we got that there? Yeah, I've got this essentially in rate as well, so in millimeters a year from that same statistical model that we use to essentially construct those time series. And essentially it amounts to a rate of sea level rise on Pohnpei of about 1.3 millimeters a year, and on Kosrae about 1.1. So I won't dwell on that one too much. But okay, so we've got sea level rising continuously on these 2 islands over the past 3,000 years at a rate of upwards of 1 millimeter a year. So why? Why is this happening? What are the drivers of sea level change in Micronesia? So to think about this, it's useful to consider all of the processes that can influence sea level in one particular place at one particular time. So relative sea level rather than, say, global mean sea level. So the first component is related to how much water is in the ocean in terms of its mass and its volume. And we can change this by melting ice sheets and glaciers, or growing them, or heating up the ocean and cooling down the ocean, which causes the water to expand and contract. And we also have glacial isostatic adjustment, which is where the land and the ocean floor moves up or down relative to what's kind of weighing on top of it. That could be an ice sheet, that could be an ocean, or nothing. So the pattern of that is different depending on where you are around the globe at a particular time. There's also a whole bunch of interesting gravitational and rotational things that are associated with ice sheets melting and glacial isostatic adjustment that I'm not going to talk about in any great capacity, but all of the GIA people complain when I leave that out. So I'll put that in there for them. I hope they're very pleased to see that I don't do any of those calculations. So these are some things that influence relative sea level. So what do we know about these processes that operate in Micronesia? What do we know about that? Particularly these ones. So I'm bringing you back to this figure that I just showed you before. because I'm highlighting a part of it that I didn't explain before, and that's what that kind of big grey ribbon and dotted line is up the top there. And this is the median and the range of a model ensemble that predicts relative sea level at Pompeii. And this is a prediction given a large range of plausible ice sheet histories and plausible solid earth models, aka like glacial isostatic adjustment models. And this is based on the ensemble compiled by Roger Creel in their 2024 Nature Comms paper on the global mean mid-Holocene high stand. Great paper if you have not checked that out already, a very important contribution to our paleo sea level field. And importantly, this prediction for Pompeii here, given these particular processes and given a whole range of plausible histories, predicts a modest high stand. So you can see that sea level is above present about 3,000 years ago, and gradually fell to present day, although there is kind of a large range of possibility here. So obviously this is distinctly different to what we have reconstructed in our proxy record, right? So this isn't necessarily explaining why we have our paleo reconstruction appearing as it is. The other thing I'll say about this is we knew that this was what's predicted for these particular islands. We know that there's a mid-Holocene high stand in other places in the Pacific. So when we were in the field, we went and had a look for other field evidence to see whether sea levels had been higher at some point in the Holocene or not, and we didn't find any evidence. So there are other parts of this equation as well that might be driving what we see in Micronesia. So there's tectonics and there's local processes. So we'll explore what those potentially could be as well. So for example, what could tectonics have to do with it? Well, we're not particularly close to any active plate boundaries here. And the volcanoes that formed these islands are extinct by millions of years. So there's no volcanic activity altering land elevation here relative to the ocean. But admittedly, we're quite poor, data poor in this region in terms of structural geology and geophysics. So but what we can suppose is that there's some sort of island subsidence going on. So we had a look at a few pieces of evidence available from the instrumental record, such as a GPS station on Pompeii. COSRAI doesn't have one. And over the period of observation, which is only the last few decades, the GPS records vertical land motion of about 1 millimeter of subsidence a year. So that's kind of on par to what we were seeing in our paleo record. And then we also had a look at what the tide gauge on Pompeii suggests when we compare it to the satellite altimetry. And that's an important comparison because the tide gauge, when that's measuring sea level, that's measuring both the land and the ocean. So it's going up and down with that, whereas satellite altimetry is only measuring the height of the ocean. So if you look at the difference between that, you might be able to say what the land's doing relative to the ocean. So the difference between these two, and this is about 1.7 millimeters a year of subsidence, that the tide gauge one is showing greater sea level rise. So, okay, there's some sort of local island subsidence happening. Okay, maybe we solved it. Or actually, let's think about some of the implications. So we've got two islands showing some over 1 millimeter worth of sea level rise each year for the last at least 3,000 years. So first implication of these reconstructions then is that it tells us a little bit more about ocean island subsidence processes. And you might be kind of going, okay, Juliet, you've gone to some ocean islands and you found that they're subsiding. Woohoo, we knew this ever since Darwin tried to write a little paper about this and the lifespan, the evolution of ocean islands, essentially. It's one of the most classic sort of physical geography processes that you might learn at school. So kind of back to basics, really, we've kind of got our hotspots rising from the mantle through into the crust, pierces the ocean floor, forms a new island. And then as the tectonic plates moving across that, you form an island chain. So when these islands move off that particular hotspot, they start to subside thermally because they start to cool down. So the crust is starting to contract, and that's causing subsidence. But then what's also not represented in this this diagram particularly well is that there's also kind of like a bathymetric swell. There's actually like a bulge on the ocean floor where there are these hotspots. So if you've got these islands on this moving plate, essentially they're going to be moving off at a particular rate, and that's going to be causing subsidence as well. But what's interesting about, we know that process is happening, and we know that that process actually has already happened for these particular islands. They're old enough that they actually should be far enough away from this old hotspot that this particular rate of subsidence should still not be happening, essentially. So essentially our reconstruction just showing, okay, we've got island subsidence happening at a much faster rate than what we would expect for that particular geophysical process. And we don't actually have any particular idea of why, but maybe generating these sorts of paleo records in some of these islands might be able to help us test some of these broader sort of geophysical processes of island lifespans, particularly in the Pacific. And oh yeah, that's the barrier reef is essentially where Pompeii and Kosrae are at in their lifespan. Essentially, they're kind of on the older end of things. But what's interesting about this process broadly is that if you've got islands that are subsiding, then that's contributing to sea level rise into the future, right? So the current IPCC projections to 2100 incorporate about 0.6 millimeters a year of subsidence, and that's derived from the satellite and the tide gauge record at the moment. But if we use our paleo derived estimate, could be as much as 1.3 millimeters a year. So that's, you know, like at least double what is in the sea level, incorporated into sea level projections in the future. And taking that out to 2100 and beyond, it technically means that you're getting a greater amount of sea level rise earlier. But importantly, this much sea level rise is very much masked and swamped by the amount of sea level rise that we are expected to get by the melting of ice sheets. So it doesn't necessarily change the projections in any really great way, but it is something to consider, and there might be other places where this difference is pretty considerable. So it doesn't change projections in a really big way. How much time have I got left? Okay, we're at like 30 minutes. Okay, we'll swing through really quickly into this particular part of it, which is probably one of the more surprising parts of this particular project for me, being a non-archaeologist and being trained as a geologist, essentially. So our sea level records had some interesting implications for trying to think about the past sort of migration and settlement patterns in Oceania. So Oceania, the story of this settlement, incredible story over, 4,000, 3,000 years. People were voyaging out from New Guinea, the Solomon Islands, and from the Philippines into different parts of the Pacific. And importantly, they went to a whole bunch of different types of islands. They went to volcanic islands where there's a lot of essentially land out of the water. They can be, volcanoes many hundreds of meters in elevation, but they also settled on a lot of coral atolls as well. But these coral atolls for 4,000, 3,000 years ago weren't actually in the current configuration that they are. And if we are assuming that sea level was slightly elevated, or there were a lot of coastal processes still operating after that sort of deglacial melt, since the last ice age, the really rapid sea level rise, a lot of these islands didn't necessarily exist even for settlement to happen. So a lot of people were heading to these high islands first before settling atolls. So the atolls settled after high islands. But if we look at the pattern here, so the pattern on this particular plot is that we've got the reds indicating older ages and the yellows indicating younger ages of first settlement. And the triangles representing high islands and the circles representing low islands. Pompeii and Khosrow, despite being high islands, are settled over 1,000 years later than other high islands in the region. Maybe that's curious, I don't know. Our proxy reconstruction, our records, suggested that we've got maybe 2.5 to 3 meters of sea level rise since that first initial settlement, about 2,500 years ago, when we see some of the first archaeological evidence on these particular islands. So we actually say, hey, maybe these islands were settled the same time as all of these other high islands in the region, but all of that older archaeological evidence is now submerged because of the really quite rapid sea level rise that has happened over the last 3,000 years. And this is the last one I'll go through before I think I have to wrap up shortly. But the other really neat thing that we think has our sea level reconstructions have implications for is cultural heritage. And on these, on the island of Pompeii and on the island of Khosrow, there are some amazing World Heritage sites. And in particular, I'll talk about Nan Madol, which is on the kind of the eastern side of Pompeii, World Heritage Site, really massive complex of buildings that are constructed out of coral and buildings that are constructed out of columnar basalt. And they were quarried somewhere else on the island, all moved to this particular site, and then constructed this beautiful array, a beautiful site of many tens of buildings, really, hundreds of buildings. It's very amazing to visit, but when Western archaeologists first came to this site, they called it the Venice of the Pacific. And they called it the Venice of the Pacific because right now it's actually in the intertidal zone. And it kind of looks like you've kind of got these buildings with canals connecting them all around them, essentially. So they kind of interpreted it as people were kind of getting around on boats across this site particularly. But if we go, okay, so this particular site was built, 800 years ago, we've actually seen a considerable amount of sea level rise since this particular reconstruction. Since this building was, these set of buildings were constructed. And if we convert that to what we found in our paleo record, there's been about 1 meter sea level rise since it was constructed. So actually, our hypothesis is, no, actually isn't the Venice of the Pacific. They actually just built their buildings on regular dry land, and it's actually this recent sea level rise that is actually starting to flood them. So understanding that, and actually that this actually might be a story of abandonment because of local sea level rise, is important for actually preserving this into the future and that cultural heritage protection, essentially, because we have not only the subsidence, but now an accelerating local sea level rise associated with the 21st century acceleration as well. I think I'm out of time now. Is that correct? If you want me to keep going, I can definitely keep going.
You can have a few more minutes because we started a bit past the hour.
All right. Then I will share one more fun thing with you. Another implication of these particular paleo reconstructions is that we can start to assess the relationship between sea level and climate drivers over hundreds of years and thousands of years. So in 2016, Bob Kopp and a lot of other researchers presented a really important paper for the sea level community that presented for the first time a global compilation of sea level records over the past 3,000 years that were kind of what they would say like a high fidelity, essentially. So, and all other global sea level curves prior to this particular one had been inversions from GIA models, essentially. So this was pretty significant. And So essentially, this was a compilation, and what we've done with our new records is use that same framework and update this global mean sea level record, but added in our new reconstructions, essentially. And this is important because this previous version that Kopp et al. In 2016 provided, and some other ones after that. So Andy Kim had one, Jennifer Walker. A lot of the data that goes into this is biased towards the North Atlantic. That's where we have a lot of these high fidelity common era sea level reconstructions, high resolution. And what we wanted to test essentially is, does it make a big difference when you add data from a completely different geographical region? Are these models biased to processes that are happening there? And we're pretty sure the answer is actually no, these models are actually doing a relatively okay job. But we're only adding stuff from one particular geographic region, and we probably need to test some of the model sensitivity to that a little bit more. But adding in new geographic data from another place doesn't impact what the global sea level curve looks like, essentially. So we can still use this and continue updating it to try and pull out some particular links between climate drivers and sea level change on a global sense. And this is important because this is essentially, these predictive models are what we use to train projections for the future. So that's pretty important. But yeah, I think I'll leave it there. This is my summary slide, essentially. I won't necessarily read it out for you, but I can leave it up while we have a little bit of a chat. But essentially, yeah, mangrove sediments, geological tide gauges, and they can tell us all sorts of things from geophysics to archaeology to global sort of climate. Yeah, thank you.
Thank you so much, Juliet. That was a fascinating talk. Yeah, reminder to the audience, you can send your questions to the questions host, who is Salman today, who would make it. You can send them either anonymously or with your name. In the meantime, we have received a few already, so I will drop them in the chat and also read them out.
Perfect.
Okay, so the first one is, increase this size. How far can you use the modern mangrove distribution method back in time? Has this been done beyond the Holocene or even beyond the Quaternary?
Oh, great question. Yes and no, in that it depends where mangrove sediment is preserved, essentially. So this is a question of because this is quite recent sort of environmental change, the sediment record is still there. It hasn't been eroded away. Whereas if you've got sea level rise and fall of, you know, many tens and hundreds of meters, that particular sediment can often be either eroded by, if it's, say, severely exposed when sea levels fall and you have kind of a river starts to, I guess, prograde out where the coast used to be, that mangrove sediment is often eroded away and not recorded. And then the same thing happens when you've kind of got sea level rise and you've got mangroves occupying a particularly, you know, completely different part of the continental shelf. But as sea level rises, that transgressive sort of erosive activity gets rid of that mangrove sediment record. But that being said, there are some unique places where we do find this. So the Sunda Shelf is a really great example. There's the really quite famous drill core suite collected from the South China Sea, and they find mangrove sediment preserved from much earlier timescales, and particularly the last sort of glacial cycle. But beyond the Quaternary, there's some fossil mangrove sediments, but it gets trickier to say, you know, exactly their sea level sort of position. But yeah, good question.
Right, that makes sense. Thanks for the explanation. Let's see if we have any other ones. Yes. Okay, this one is also about mangrove, and it asks, do different mangrove species have somewhat different growing environments, or are they all broadly similar?
Also a very good question. This is it's that's quite a local sort of specific has a local specific answer really. So there are a lot of different mangrove species. For example, in the Indo-Pacific, there's like I think probably even hundreds, and they depending on what they've evolved to like, essentially. Some of them will live in different parts of the intertidal zone. Some of them will live in different climates. So when we think about that for sea level, it's quite helpful because there might be a particular species that produces a particular pollen that only lives in this narrow part of the elevation zone of the intertidal zone. And there might be another one that lives at a much lower elevation in the modern environment in the intertidal zone. And if we can use those sort of say pollen indicators to say, okay, it was here versus there, then that makes our reconstruction much more precise. But yeah, so you sometimes see mangrove zonation associated with those sort of preferences that each species has.
Thank you. Okay, great answer. We have another anonymous, quite quick question, I think. They ask, great talk. I couldn't see the chart in detail. What is the uncertainty in sea level estimates, either in meters or centimeters, that you can obtain from these mangrove deposits?
Yeah, good. Also good. And yeah, I didn't detail that. And I probably should have, to be honest. But yeah, uncertainty for say the Micronesian mangroves. When we are very conservative about this, it can be like 1.5 meters, 1.7 meters, for example, and that uncertainty largely comes from the tidal range itself. So if you have mangrove sediments that are accumulating in, say, a microtidal location where the tides only range, 20 centimeters or so, then your uncertainty on your reconstruction is going to be less. If you're in a macrotidal place where you've got, mangrove sediments accumulating over, 3-4 meters of elevation, then that sort of uncertainty is going to be much larger in your then that's kind of coming back to the previous question. If you can use things like pollen to narrow sort of that sort of depositional environment range that you're looking at, then you can improve your uncertainty on that essentially.
Interesting. And if I can add to that, how do you estimate the tidal range or the tidal regime in the past? Do you use like sedimentological markers, or to know whether it's micro or macro tidal?
Yeah, so this is an assumption that us paleo sea level scientists sometimes make, is that the tides are the same in the past, and we know that that's not necessarily true because paleogeography is changing, which means that the tides are very much changing as well. A lot of people will try and do some paleogeographical and tidal models associated with that to correct for that, but otherwise that is an assumption that we take, that it's modern. Yeah.
Right. So if an island is microtidal right now, you're assuming it's also mostly microtidal in the past.
Absolutely.
That makes sense, because I think that within an island, the major geometries don't change. That much.
In like a big sort of bay, it's a bit more problematic, but yeah, these islands, I wouldn't expect there to be a great tidal shift, I would think. Maybe. Yeah.
I wouldn't know, but that's very interesting. Thank you.
No worries.
Okay, this is a fun question. They ask, regarding the human migration story, is there some kind of underwater archaeology happening at these sites that could uncover like these potential flooded archaeological sites?
Yeah. So there have been, and this is the case in a lot of places around the Pacific, there have been during like dredging for construction or something, they've found a lot of submerged artifacts. So there's definitely submerged archaeology out there. But as for like a current push to do this, no, not necessarily. So I think some people have done a little bit of diving and but I don't think it's published in any great capacity, but some people have done a bit of diving around Nan Madol to kind of have a look at whether there's other sites essentially. And the motivation for that was the I guess the creation story that has been passed down through oral history about Nan Madol. And I think the story of why it got built, or part of the story of why it got built, is one of the chiefs at the time was like standing on a hill and looking out over this bay where it first got where Nan Madol was eventually built. And it said that he saw something like an underwater city like out there, and that they wanted to build next to this. So people have kind of gone to try and look for, almost like this, Atlantis kind of thing, but I don't think anyone's found anything per se, but doesn't mean it's not there, but yeah.
Oh, that's fascinating. We got a couple more questions. Copy paste it. Next question asks, do you plan on doing similar measurements across more islands of Micronesia?
So we did have a look at the Chuuk archipelago, which is another sort of similar volcanic island to the west of Pohnpei, but there doesn't seem to be the same rate of vertical land motion, aka subsidence, and that's important when we think about the mangrove sediments, because we actually need that accommodation space generation for those sediment archives to accumulate. So when that doesn't happen, we don't really see very thick sediment sequences of mangrove peat. So we can't essentially use this techniques there. And that's the case where for a lot of some of the other, particularly coral atoll type islands across Micronesia. But we did do some of this work in Samoa, where there is accommodation space generation because some of the islands are subsiding, related to different tectonic types of activities than what happens in Micronesia. But yeah, there's definitely scope to use this in a lot of different places, I think.
Cool. Okay, so far I have one more question, so quick reminder to the audience that if you have any questions, to send them to us. But they ask, great talk. What about the transportation of mangrove-produced pollens? Are they getting deposited at the same place, or can they be transported some distance?
So good question. Yes, they can be transported, very much so. But there are a lot of species that seem to produce really low amounts of pollen, and based on modern sort of trap and also surface sediment studies, appear to stay pretty localized. So I think it's a very site-specific thing again, where there might be some mangroves where they produce a lot of pollen and it gets remobilized quite a lot. And like, for example, there's the family Rhizophora. They are wind pollinated species, so they produce a lot of pollen, and therefore it can get transported a bit more regionally than, say, an Abyssinia mangrove species, which seems to produce hardly any, and then when it does, it's quite localized because it's vector pollinated by insects or by birds or those sorts of things. So so it's not perfect essentially, but it's one of the tools in our suite of techniques that we can apply. Yeah.
Okay, thank you so much. again, I think that was the last question. I'm gonna wait a few more seconds if anyone really wants to ask a final question, but we're getting close to the top of the hour
Great questions,
anyway.
everyone. Yeah, very good.
So if there is no more questions, if you also otherwise have a question, you can keep it for the tea time. Then I want to thank you again, Juliet, for a great talk. Nice to have someone from Australia and this part of the world. It's usually not so easy to organize that, considering we are mostly
Thank you for having
based
me.
on the other part of the world. No, we did hear from people that listen that they would like to have more representation across the globe. So we try to do that.
Great.
So with that,
Thank you.
I will end the talk. I will have a quick more announcements to make before we officially end the talk, and then we can go over to tea time.
Great.
Okay,
Thank you. Thank you, Nina. Thanks for facilitating.
Thank you. No problem. We like doing this. Yeah, thank you again, Juliet. Thanks everyone for joining. Please fill out the weekly feedback form. Again, if you can, we would really appreciate that. And then next week we are back at the usual time and place with a talk about macroecology. More details will follow soon by Bethany Allen, who is based at the GFZ Helmholtz Center for Geosciences in Germany. So for everyone who is not joining for tea time, I hope to see you next week. Have a great rest of your day. For those that are staying, we always have some kind of icebreaker question. So this week it is, what is your favorite coastal environment? And why is it mangroves, of course?
It shouldn't be mangroves. It's not fun. It's not fun to be in them. I'm not gonna lie.
Pick something else, not mangroves. So then before we go into tea time, we have a quick break for around 2 minutes, so you can walk around a bit, turn off your camera for a second and breathe a bit. Then I'll stop the recording.
I'll just get a drink of water.
Yes, so hope to see you, some of you soon, and otherwise see you next week.